Last time, we cut a bar open and found the internal force, then turned it into stress and strain. But before we can find that internal force, we need to know every external force acting on the structure. Where do the forces come from? How does a beam know it's being held up? Those triangles at each end are supports, and each one pushes back in a very specific way. Today we'll learn the types of loads, the types of supports, and how to find every reaction force. That skill is always step one in solid mechanics, so let's build it carefully. A force isn't just a number, it's a vector with magnitude, direction, and a point of application. Here's a force applied at a point, pulling up and to the right at some angle theta. In 2 dimensions, we can break any force into a horizontal part and a vertical part. The horizontal component is F sub x, and the vertical component is F sub y. F sub x equals F times cosine theta. F sub y equals F times sine theta. This decomposition turns every angled force into 2 perpendicular components, and that makes equilibrium straightforward. Now let's look at the different ways a load can act on a structure. There are 3 main types of loads you'll see in this course. First, a point load, a single force applied at one location measured in newtons or kilonewtons. Second, a distributed load, force spread over a length like snow on a roof. We measure it in newtons per meter. Third, an applied moment, a pure twist with no net push. Units are newton meters. Distributed loads need special attention because we often replace them with a single equivalent force. Let's see exactly how that replacement works. A distributed load is harder to work with than a point force, so we convert it. For a uniform distributed load, same intensity everywhere, the total force is W times L. R equals W times L, and it acts at the midpoint of the loaded length. For a triangular load that starts at 0 and grows to a peak of W naught, the resultant is different. R equals U naught times L over 2, acting at 2/3 of L from the 0 end. This equivalent force gives the same reactions. But remember, it's only valid for finding support reactions, not for internal forces. Now we know how loads act on a structure. Next, how does the structure push back? A support is any connection that prevents a structure from moving, and each type resists motion in a different way. A pin support allows the beam to rotate, but it can't slide in any direction. That gives us 2 unknown reactions, a horizontal force and a vertical force. A roller support can rotate and slide along the surface. It only pushes perpendicular to that surface, so just one unknown, usually vertical. A fixed support locks everything. No sliding, no rotation. It gives us 3 unknowns, horizontal force, vertical force, and a moment. So a pin gives 2 unknowns, a roller gives 1, and a fixed support gives 3. Memorize those numbers. They tell you how many equations you'll need. And that brings us to the idea of static determinacy. In 2 dimensions, we have exactly 3 equilibrium equations. Sum of forces in x equals 0, sum of forces in y equals 0, sum of moments equals 0. That means we can solve for at most 3 unknowns using equilibrium alone. A beam with a pin and a roller has 2 plus 1 equals 3 unknowns, exactly 3 equations. That's statically determinate. 2 fixed supports give 6 unknowns, more than 3, so equilibrium alone isn't enough. That's statically indeterminate, and we'll handle those later. The rule is simple. If unknowns equal equations, you can solve the problem with equilibrium. Let's apply all of this to a real structure, a simply supported beam. Before you touch any equation, you must draw a free body diagram. That's a sketch of the structure showing every single force. Here's a beam with a pin on the left, a roller on the right, and a downward force in between. Step 1. Mentally remove the supports and replace each one with its reaction forces. The pin gives us a sub x and a sub y. The roller gives us b sub y. That's 3 unknowns. Step 2. Label every point and every force. No ambiguity. Step 3. Count your unknowns. 3 unknowns, 3 equations. We can solve this. Once all forces are visible and labeled, you have a complete free body diagram. This is the foundation of every problem we'll ever solve. Now let's put everything together in a full worked example with real numbers. A beam is 5 meters long with a pin at A on the left and a roller at B on the right. An 8 kilonewton point load acts downward at 2 meters from A, and a uniform distributed load of 3 kilonewtons per meter covers the full span. Step 1. Replace the distributed load with a single equivalent force. 3 kilonewtons per meter times 5 meters gives 15 kilonewtons acting at the midpoint, 2.5 meters from A. Step 2. Identify the unknowns. The pin gives a sub x and a sub y. The roller gives b sub y. 3 unknowns, 3 equations. Step 3. Take moments about A. This eliminates both a sub x and a sub y in one equation. The 8 kilonewton load at 2 meters and the 15 kilonewton resultant at 2.5 meters both cause clockwise moments. B sub y at 5 meters acts counterclockwise. Solving gives B sub y equals 10.7 kilonewtons upward. Sum of vertical forces gives a sub y equals 12.3 kilonewtons upward. And sum of horizontal forces. There are no horizontal loads, so A sub x equals 0. Let's verify. 12.3 plus 10.7 equals 23, which matches 8 plus 15. The solution checks out. Now you can handle loads, supports, and free body diagrams, the essential setup for every problem. In the next episode, we'll use these tools to solve full equilibrium problems on rigid bodies, including frames and multi-part structures.